Hi everybody, welcome to another video in statistics, section 5.3, independence and the multiplication rule. Right, two events A and F are said to be independent if the occurrence of event E does not affect, so occurrence of E does not affect the probability of event F. Two events are dependent if one thing occurs will affect in the other. Right, well, let's look at these two examples. Suppose that two 40-year-old women who live in the United States are randomly selected. The event that women 1 survive the year and the women 2 survive the year are independent. So we picked out two of them. The probability that they will survive a year for each one survive year are independent. Now, if we not select two of them at random and we select two of them from the same apartment complex, then the event women 1 survive the year and women 2 survive the year are dependent. Because if both of them living in the same apartment complex, let's say there's something happened, an accident, maybe the apartment complex are built in the same home, or they got on fire, or both of them travel on the same street and get in an accident. So those things that possibly happen because they live close to each other, so they might experience some event that let them survive or not survive the event, or maybe some kind of a pandemic outbreak and both of them got sick at the same time. So those things more likely to happen if they live in the same apartment complex. So those, because of that, these two events are independent, and those two events are dependent. The other one, when we select two randomly, are independent. So independent when they're not affecting each other, and dependent they might have affect each other. Right. The reason that we say that when we select two of them randomly, because in the United States there will be millions and millions of 40-year-old women. So we select two of them, as the chance for those two to be close to together are very slim. So that's why we said that independent. Right, here's some example. Determine which of these are independent. Suppose that we draw a card from a standard 52 card deck. So we have a deck of 52 cards and we pick one of them. And then we roll a dice. A dice have 6 faces. So of course that different things. So that's certainly independent event. So whatever we have in the card doesn't affect a die. Right. Now the second event. There are 30 chocolates in a box, identically shaped. There are 11 filled with nuts, 10 with caramel, and 9 with solid chocolate. And you select one piece, eat it, and then select the second piece. Are the event of getting a chocolate filled with nuts the first time and getting a chocolate filled with nuts the second time independent? Right. Or something like this, it will be easier if we draw what we call a tree diagram. Or later on we try to put that more compact and we draw that in the spot, in a slot, I should say. Alright, so first, if you want to pick the first one, there will be 3 possible outcome. Filled with nuts, filled with caramel, and solid chocolate. That's the first choice. Now, not only that, the tree diagram will list all the possible outcome for the first one, and the probability of getting a nut on the first one is 11 out of 30. 10 caramel, and last will be 9 with solid chocolate. 9 over 30. Next, and then when you select one of them, eat it, and then we do that again for the second time. Right, for the second time this may be nut, caramel or solid. Now different things here is if we eat the first one, it is a nut, then there will be only 9 left, and there will be 29 total chocolate left. If we eat the first one is nut, there's still 10 caramel left, so it will be 10 out of 29, and the last one will be still 9 solid left, but out of 29. So it depends on what we have in the first one. The first one getting a nut is 11 out of 30. The second one getting a nut we depends differently with 3 different scenarios. Now, if the first one is caramel, we still have 10 nuts out of 29 nuts, or 10 nuts out of 29 chocolate. If the first one is caramel, we only have 9 left out of 29. If the first one is caramel, we still have 9 solid out of 29. Right? So 3 different scenarios. Again, if the first one is solid, we still have, alright, sorry, if that is 11, there will be 10 left. If we select the first one, so there's still 11 nuts. So if the first one is solid, we still have 11 nuts out of 30. If the first one is solid, we still have 10 caramel out of 29. And if the first one is solid, we only have 8 solid left out of 29. So what we choose on the first one definitely affect what we have on the second one. Depends on what we have here, that will affect what we have on the second one. So this is not independent. But when we write the tree diagram here, we can later on do a lot more interesting math with it. But for now, this is not independent. Or if it's not independent, we can say they are dependent. Right, another example. A fair coin is tossed. Are the event of getting a tail on the first toss and getting a tail on the second toss independent? Well, we assume that a coin is tossed gently. Then the probability of getting a tail on the first one is the same as probability of getting tail on the second toss, unless it is the coin, and when instead of tossing, you throw very hard on the ground, and the coin bend, or for some reason one surface damaged badly, then the weight distribution will not be the same as original. In that case, it will be dependent. But if you just toss them gently like this, the probability of getting the first one or the second one will be the same. Whether it is a fair coin or not, the probability of getting the tail on the first one will be the same. If it's not a fair coin, and let's say you only have 40% chance of getting tail on a toss, then the second one or the first one is still 40%, whether it's a fair coin or not. So in this case, it's independent, unless after the first toss the coin is destroyed, then that will be differently. But other than that, it is independent. Right, next, multiplication rule for the independent events. Later on we see that whether it is independent or not, we still can apply the multiplication rules. Right, probability that a randomly selected, let's say E and F are independent event. If they are independent, then probability of E and F, I just multiply. Now, that's rather confusing, right? We had probability of E and F earlier. What is the difference? What is the difference of, sorry, need to find it. what is different of this, not that, yeah, what is different of the P of E and F in this problem and probability of E and F in this problem? So the thing is, when we talk about the addition rule in the other formula, we still have E and F, but in that case, we only have one trial. If we're tossing a coin one time, the probability of getting a tail is 50%, a probability of getting a head is 50%, so the probability of getting a head or a tail is 0% because you cannot have both. Right, now let's say an example for a deck of cards, 52 cards. If you pick the first card is an ace of hearts, 1 out of 52, and you put it back, and then the probability of getting an ace of spade of club is also 1 out of 52. So the probability of getting one of these two cards is what? So sorry, a little bit confusing. Now let's go back to 52 cards. The difference between the formula earlier and this formula is depends on how many cards we pick. Right? If we pick out one card, let's say I pick this one, the probability of getting a king is 4 out of 52 because there are 4 kings out of 52. The probability of getting a club is 1 out of 13. Now, the probability of getting a king and a club is 1 out of 52, right? So a king and a club, or in this case, a king of club. So that is only one trial. We only pick one card, and one card happen to have two two characteristics or two properties of a king and a club. One card. When we talk about that case, if that is the case, then it is we're talking about picking one card. It will be this formula. This is only one, or we call the one trial. Now, this formula involving two trials. So let's say just scramble the card, and the first one is a 9 of diamond, and if we scramble again, and we pick out again, the probability of getting this again is 1 out of 52. Originally it is 152, the second one also 1 out of 52. So those are independent events. So that in this case, when we use the independent, that will be two different trials, or pick the card two times, as opposed to for the other case we pick one card that has two properties. So now we focus on the independent event. Now, the probability that a randomly selected female aged 60 years old will survive the year is 99.186. What is the probability that two randomly select 60-year-old female will survive the year? So rather than draw the tree diagram where we said a female survive a year and not survive a year, and then the second survive, not survive, we can just draw a slot. So let's say they survive for the first woman and survive for the second one. We have 99.186, or I put in decimal, for the first woman to survive the year is that much, and then the second to survive the year is also the same thing. because there will be like millions and millions of those. When you pick one out, the second one, even though there's one less than originally you chosen, but we still have millions and millions left, so the probability is about the same. So we just multiply them together, just like this formula say, and we just have 0.99 0.99186 times itself, or if time itself we just say square, and we have 0.9838. So what is the probability of 2 randomly select women will survive a year? Will be this much. So because the first one doesn't affect the other, because we choose randomly out of millions and millions. Right, here's another example. Manufacturer exercise equipment know that 10% of their products are defective. They also know that only 40% of their customers will actually use the equipment in the first year after it is purchased. So if there is 1 year warranty on the equipment, what proportion of the customer will actually make a valid warrant claim? So I just said there are two things here. One of them is the product are defective, and the second one, the customer will use it or not. By the way, this should be independent, because when the customer buys a product, with that person has no idea if it is defective or not. Right, so of course we buy the equipment, and then actually we practice, we use it within the first year. Of course, if you buy it and you use that in the second year, you cannot claim it, right? So the only percent of the population that can actually claim it is, number one, they have to buy a defective equipment, and number two, they actually have to use that in the first year. So those two have to be happened. So if we want to test rod, the first condition that it have to be defective, and getting a defective is only 10%. Now the second chance, the second thing have to happen is that have to use in the first year. And then 40% of those who bought actually use it. So when we multiply them, and that gives us 0.04 or 4%. So only 4% of them actually will make a claim, because they buy a defective one and they know it is defective because they actually use it. Right. Of course, we assume that it is independent. So if we want to draw the tree diagram, it will be like this. So first we get a defective one, or not defective. And after that, we can use in the first year or not. We use in the first year or not. Now, getting a defective probability of 1%, I mean 10%. Getting not defective, of course, the complement to that, 90%. 1 minus that. So those two always set up to 1. Now, using the first year, there's 40%, and not using is 60%. So using the first year is 40%, not using it 60%. Now we have the tree diagram. After we have the tree diagram, we just trace from the beginning to the end. Let's say we want a valid claim, so they have to be defective and have to be used on the first year. So we take those numbers that along this tree diagram, 0.1 times 0.4, give us that. So when we draw the slot like this, we only take one specific path of the tree diagram. Right. Next, suppose that you can choose one type of meat are 4 possible choices: beef, chicken, pepperoni, and ham. And 1 type of vegetable are 5 possible choices: pineapple, mushroom, onion, spinach, and green pepper to put on the pizza. If you choose randomly, what is the probability of getting a pizza with pepperoni and mushroom? So the first one is the meat, and you get pepperoni. And there's 4 meat, so there will be 1 out of 4. The second one is the vegetable, and there are 5 vegetables, and you can choose only 1 of them if you choose randomly, and it happened to be mushroom. So again, what you choose on one doesn't affect the other. So randomly, I mean, they are independent events. So we just multiply them. 1 over 4 times 1 over 5. When we multiply fraction, multiply straight across. And 1 divided by 20 is 5%. Yeah, to just give a slot of the probability of each trial, and it will multiply everything. Right. And of course, we can have more than 2 events. In that case, if they are independent, we just multiply all of them. So just make the slot like this, and then put each probability in, then multiply all of them. Right, here a few more examples. Suppose a test has 10 true-false questions, and what is the probability that a student gets every question and get 100% correct on the test? Well, so there will be 10 questions, 10 slots. That's 5, 6, 7, 8, 9, 10. And each question only true false. And if we guess, the chance to get incorrect is 50%. So we have 0.5 for each one of them. And so we multiply them. Because if we just guess randomly, then the probability to get all of them correct would be just multiply all of them together. And 0.5 times 0.5 times 0.5, 10 times. Just say that to the 10. Or if instead of 0.5 we say, how about 1 over 2 times 1 over 2 times 1 over 2, 10 times. So that is 1 over 2 to the 10 power. The 10 power goes to the top. Sorry. So 10 power goes to the top and then go to the bottom. So that gives us 1, 2 to the 10 is 1024. So that's what we have. 1 divided by 1024. I'll be that much. So 0.000. But this number, what does that mean? E, that E means times 10 to negative 4. So if we want to get rid of that, we move 4 places to the left. 1, 2, 3, and 4. Decimal will be there. And then we have to fill in the 0. So that would be 0.0000976. That. So we'll write 0.12397. Right? So again, when we see this with the negative, we move the decimal to the left 4 places. In this case, negative 4, so move to 4 places to the left. If this one positive, we move to the right. For example, if this, so we move 1, okay, 1, 2, 3, 4, 5. So that's what we have. This will be equal to 1, 2, 3, 0, 0, 0. So if it's negative, we move the decimal, the same number to the left, and then add 0 to it. Right, next, suppose that the probability of getting a damaged hailstorm in a year in the city is 1%. What is the probability that the city has no damaged hailstorm in 5 consecutive years? Right, so we have 5 years, 5 slots. So the first year when we get a damaging hailstorm is 1%, right? Only 1%. But this is that have no damaging hailstorm. So if we don't have, if we're getting a damaging hailstorm is 1%, not getting it will be the complement. So 99% of not getting a damaging hailstorm by complement. 1 minus 1% is 99%. And you want that for 5 consecutive years. So we have 0.99 to the 5th power. Can we change this to fraction? No, so we just leave at that, about 95%. Right, so we just keep the slot. Because if we have the tree diagram like this and then 5 different states, the tree will be very messy. Right, next, as you see, when we approach this, there's no longer considered classical probability because the outcome they don't have are not equally likely. In this case, 1% getting a hailstorm and 99% not getting a damaging hailstorm, right? So they are not equally likely. 1% and 99% completely different. Right, we have the same example earlier. The probability that random selected female 60-year-old will survive years, that much we only talk about that. What is the probability that 4 of them select randomly will survive the year? So we just 4 slots. In this slot we have 0.99186, 0.99186, 0.99186, and so we have that to the 4th power. And it's not going to be fraction, so I'm just going to say 0.9678 or 96.78%. Next, so that is the probability of all 4 will survive the year. So I just say all 4 survives equal to that. Now, what is the probability at least 1 of 4 randomly selected female will not survive the year? Right, now this will be complicated. If we're doing the slot like this, and this is at least 1, so that could be 1, could be 2, could be 3, could be 4. So let's assume that the first one survive, but the second one is not. If it's not, we have to take the complement. Right, so let's say the second one does not, and the third one survive, and the third one. So there are too many different scenarios we have to list. And the case here says it is at least 1, so it could be 1, 2, 3, and 4. What it cannot have is 0, which we have here, right? So we say all survive, meaning 0 death, or 0 die, or 0 death, that's fine. It is complement to at least one death. Not survive here mean death. If we write that, so these two are the same, which is complement of these two, at least one death, or we say 1, 2, 3, or 4 death. So they are complement to each other. So probability of at least one not survive or just one death is 1 minus probability of 0 death. 1 minus this. So that's 0.0322. Finally, the probability that it will rain is 40% each day over 4-day period. What is the probability that it will rain at least 1 in 4 days? So this is when we see at least something like that. That is a signal that probably it will be easier if we find a complement event. So it will rain at least 1 of the 4 days. So complement to at least will be none. Complement to at most will be, complement to at least 1 is none. Right. If it is 1 or more, and other than that, the last case is 0. So first we have to find the complement to it. So be all, or be if we want 1 of the day would be raining, so the complement would be no rain in 4 days. There will be 4 slots, and each one, if the probability of raining is 40%, not raining will be 60%. Right? Raining is 40%, not raining is 6, and we have not raining in 4 days. So we multiply all 0.6 times 0.6 4 times, or to the 4th power. Can we put it in fraction? Yes, but let's just give it 0.1296. Now, the complement to this is at least 1 rain at least 1 day, right? So before that I say rain in at least 1 day is complement to no rain, right? Because of that, probability of rain in at least 1 day equal to 1 minus probability of no rain. So 1 minus that. So we have that. So every time we see at least, well, or at most for that matter, see if we can use the complement and calculate what is the complement to that first, and then we subtract it from 1. Sometimes like that will be easier. In the last 2 examples, that is the case. Right, with this I stop this video here. See you in another video in statistics. As always, thank you for watching.